Good afternoon, everyone. So today's session we'll discuss about an Hamiltonian circuit problem. So again, this Hamiltonian circuit problem will uses the concept of an backtracking, and already all of you know that how the backtracking concepts work. Okay, the backtracking concepts will be usually used when we wanted to find out a set of the solutions. So it will move on a one particular path and try to find out the solution. If it is not finding the solution, it will go back and try in another path, or even though it is getting a solution on a one particular path, it will try out in another path in order to get an one more solution vector. So usually backtracking is used when we wanted to find out a set of the solutions. Okay, and last class I already explained you about an n-queen problem and also an sum of the subset problem. So today we'll discuss on one more problem, that is an Hamiltonian circuit problem. What is this Hamiltonian circuit problem? It is a problem so where you will start with an one particular vertex and visit all the other vertices exactly once, okay, and come back to the same vertex. So that is a Hamiltonian circuit, or the Hamiltonian cycle usually we will call. So here you will be given an that is an undirected, you will be given an undirected connected graph. Okay, you have to start with a one particular vertex, visit all the other vertices exactly once and come back. It is similar to the TSP problem, but TSP problem you will be searching for a minimum cost. Here you are not searching for any minimum cost, just we are checking that whether the cycle exists or a path exists or not. Okay. As you will be knowing that all these backtracking concept, you will be constructing the solution space tree or a state space tree, how we have constructed for the sum of subset and n-queen. In the same manner we are going to construct the solution space tree or a state space tree for the Hamiltonian cycle also. So suppose if this is the given graph, so what we will do here, assume that the starting vertex is a 1. So from 1 there are two outgoing edges are there, 2, 2 and 4. So there are two paths I can move, 2 and 4. Now from 2 already 1 is visited, so only the option what you are having is the 5. So from 2 it is only the 5. Next from 5 there are two outgoing edges are there, one is for 4 and other one is for the 3. So one is for the 4 and the other one is for the 3. Now from 3 I can visit 4 and 5, but 5 is already visited, so only the option left out is 3 to 4. Okay, now all are visited. See here, 1, 2, 5, 3, 4. Now I wanted to check, are you having a path from 4 to 1, because I have to come back to the same starting vertex, no? So whether there is having a path from 4 to 1, we are checking 4 to 1. So that means we have traveled from 1 to 2 and 2 to 5 and 5 to 3, 3 to 4, 4 to 1. So I got a one solution, one Hamiltonian cycle, one solution vector what we got, that is this one. Okay, now again after getting the solution here, I will move back and again I chosen and one more path here, that is 5 to 4. Now from 4 there are three options. One is for 1, but already one is visited, and other one is for 5. It is also visited in this particular path. Only the other node which is unvisited is 3, that is 4 to 3. So 4 to 3. Now all are visited. 1 is visited, 2 is visited, 5 is visited, 4 is visited and 3 is visited. I need to come back to the vertex 1, but I cannot come back to the vertex 1 because there is no path from 3 to 1. Therefore this is not a solution. Again I will backtrack and I will go for a one more option, that is 1 to 4. Now when I am moving from an 1 to 4, and from 4 there are two options are there. One is for 3 and the other one is for 5. One is for 3 and the other one is for 5. Now from the 3 I am having only this 5 option. So it is only one option here, 5. And from 5 I am having 4, 1, 4 and 2, but already 4 is visited in this particular path, so only 2. So 5 to 2. Again from 2 come back to the 1 because already all are visited in this particular path. So this is one more Hamiltonian cycle what we got. Now again I will backtrack and I will move to the one more option. What is that? 4 to 5. So when I am moving from 1 to 4 and 4 to 5, now two options are there, 2 and 3. So 2 and 3. Now from the 2, only option is for 1 and 5, but both 1 and 5 are already visited in that particular path. So I cannot move. Then from 3 I am having 4, 5. Okay. From 3 we are having to the 4, 5, but already 4, 5, both of them we have visited in this particular path. Therefore, from 3 and 2 I cannot move anywhere. So we cannot find the solution here. So this is how we will be constructing the Hamiltonian cycle. Got it? How we are constructing the Hamiltonian cycle. Start with any of the vertex and visit all the other vertices exactly one and come back to the same vertex. So that is called as an Hamiltonian cycle. And this is a solution space tree or a state space tree what we have got. Now let us consider this particular graph. Okay, so it is a little bit lengthy here. So from A there are three options, 1 C, B, C, F. So from A, B, C, F, three options. Again from B, you are having to A, but already A is visited, so F and D. From B it is D and F. From B it is D and F. Now if I will move on to this particular path, I am having an option to the F, C, E. None of them they are visited, so F and E. Okay, C is visited in this path. It is A to B, B to D. So it is A to B, B to D. Now from the D I am having to the C, E and F. Okay, so E and the F. Why not to the C? From D I am having one more option I have to write. I think I forgot to write that one. So see here, from the D I am having to the E, that is this, having to F and having to the C. So three options are there. So you need to write all the three options. And from F you are having to the A and B, but A, B are already visited. Two more options, C and the D. So it is C. From here it will be having a D, and from the C it is, no, from F it is to the C and D. So to the C and D. Again you go in this particular path. So like that. Okay. So how many outgoing edges are there? You go through that outgoing edges and consider only the unvisited vertices. Consider only unvisited vertices. So I will consider this particular solution here vector. So A to B I am moving and B to D. So from the D you are having two options, E, F and the E. So I am moving on to the E. So already A is visited, B is visited, D is visited, I am in the E. So from E I can go to the C and D, but D already visited, so only the option left out is the C. And from the C you can move to the A, but already visited, then F and the E and the D. So there are four options are there, but almost all are visited here. A is visited, B is visited, F is visited, C is visited. So, sorry, here no, D is visited, E is visited. So from the C only the option here, because F is also visited, D also visited, A visited, only the option is from C to an F. Okay. Now for F to A, are you having a path? Yes, F to A we are having a path. So that is one Hamiltonian cycle what you are getting. So like that we need to travel from one vertex to the another vertex and find out any solutions you are getting it or not. And these are all the 6 solutions. These are the 6 solutions what you are getting for this particular problem. It is very lengthy. So try to write it in a horizontal way instead of writing it in a vertical way. So in the exam you and in the internal try to write it in a vertical way. Okay, because there are 6 vertices are there. So obviously it will be an lengthy. Okay. So now we will move on to the algorithm. Okay. Now I'll consider this Hamiltonian algorithm. So before I'll go to this particular algorithm, you will not understand anything if directly I'll move to the algorithm. So you should know these two conditions whenever you will be on designing designing the algorithm for this Hamiltonian cycle. You should know these two conditions. So before that one, you will be on reading the adjacency matrix. It is not a cost adjacency. You just make a change here. So it is just an adjacency matrix you are reading. And initially for all the vertices, I am setting the values as an 0 except for the vertex 1. Okay, because it is a source vertex. So except for that one, the rest all the entries in the solution vector, we are making it as a 0. Then after that one, from the second vertex and all, we will go on call. So that we will see it in the algorithm. So the two conditions that you have to satisfy when you want to find out the new vertex in the Hamiltonian cycle is that, so whatever there should be a path from the previous vertex to the, see, assume that if I am considering this as a vertex, okay, this as an vertex, then their current vertex is this one. There should be a path from the previous vertex to the current vertex. That is one condition. Other condition is that the vertex, current vertex, whatever you are considering in the Hamiltonian cycle, it should be distinct from the previously selected vertexes and it should be an unvisited vertex. So these are the condition that has to be satisfied. What are those conditions? Assume that this is a current vertex, what I wanted to consider in the Hamiltonian path. Then there should be a path from previous vertex to the current vertex, and this vertex should not be a repeated vertex, it should be a distinct vertex, and it should be an unvisited vertex. It should not be an visited vertex. Then I can consider this vertex 5 as one of the vertex in the Hamiltonian cycle. Getting my point? So I can consider any vertex as a vertex in the Hamiltonian path if and only if it is distinct vertex, it should be unvisited vertex, and there should be a path from that current vertex to the previous vertex. Current vertex to the previous, there should be an path. Only if these two conditions are satisfied, then only I can consider that particular vertex as a vertex of the Hamiltonian cycle, Hamiltonian path. Okay, then only I can consider that particular vertex. Which vertex? Which is satisfying these two conditions. What are those conditions? So it should be a distinct vertex, unvisited vertex, there should be a path from previous vertex to that current vertex. Then only I can consider that current vertex in the Hamiltonian path. Then after that one, what you will do, so you will check that whether that vertex, whatever the current vertex you are considering, it is a last vertex. Okay, so among all the 5 vertices, already I have visited all the vertices and I am visiting the last vertex. Suppose like 1 to 2, 2 to 5, 5 to 3, 3 to 4. Now all are visited, I am in the vertex 1. Then finally what I have to check, are we having a path from 4 to 1? Are we having a path from 4 to 1? That we need to check. So that is also we need to check. So whether from last vertex, whatever we are having, the last vertex which is our current vertex, are we having a path from this to this? So I need to repeat that same procedure in order to find out the all such type of the possible solutions. And so got it, that is the condition. So what is that condition? So any vertex I can consider as a vertex in my Hamiltonian path only when it is distinct vertex, unvisited vertex, and there should be a path from previous vertex to this vertex. Then only I will consider that vertex as a one of the vertex in my Hamiltonian cycle. So before I will move on to the algorithm, I will tell you how to trace that. So initially, for how many vertices are there in this example if I will consider? So 5 vertices are there. So initially make all of them as an 0, 0. So since I am considering the first vertex as an source vertex, so I will assign it as an 1. Okay. Then what I will do, here in the each iteration what we are doing it here is, we will be considering the next highest vertex. So assume that 0 is a vertex, next highest vertex is the 1. So is it is a visited vertex? No. Is it is a distinct vertex? Yes. Okay. So then initially I will consider that one. Next I will call the Hamiltonian of the 2. So when I will call Hamiltonian of the 2, again it is initially 0. I will move to the next higher vertex. Now I will consider this vertex 1. Now I will check that are you having a path from previous to this? Yes, 1 to 1 there will be a path, 2 to 2 there will be a path, 3 to 3, like that only we will consider. So now 1 to 1 path is there, but this is not a distinct element. 1 is already repeated in this previous path, previous vertex what we have considered, it is same. Therefore, this cannot be the vertex in the Hamiltonian cycle. Then I will consider a next highest vertex, that is 2. Now, are you having a path from previous to this? Yes, 1 to 2 there is a path. Is it is a distinct vertex? Yes, it is not repeated in the path. And is it is an unvisited vertex? Yes. So, this will become one of the vertex in my cycle, Hamiltonian cycle. Then I will call the Hamiltonian of 3. When I will call Hamiltonian of 3, again it starts with 0, move to the next higher vertex, but it is already repeated in the path. It is already repeated. Here already 1 is there, repeated. Then I will take the next highest vertex 2. It is also repeated in the path. My path is now 1, 2. Okay, it is also repeated. Now I will consider the next higher vertex, that is 3. So is it is a repeated vertex? No. Okay. Is it is an unvisited vertex? Yes. But are you having a path from 2 to 3? Because I told you that condition there should be a path from previous to the current vertex. So you are not having a path from 2 to 3. Here there is no path from 2 to 3. Therefore I cannot consider this as an vertex in the cycle. Then I will move to the next higher vertex 4. So 4, again 4 is not repeated in this 1 and 2. It is a distinct unvisited. Are you having a path from 2 to 4? So 2 to 4 there is no path, direct path is not there. Therefore again move on to the next higher vertex, that is 5. So again 5 is not repeated in 1, 2. Then are you having a edge from 2 to 5? 2 to 5 edge is there. Is it is a distinct unvisited vertex? Yes. So I will consider next that as the vertex in my path. Then I will call the Hamiltonian of 4. Again 0, 1 is repeated in the path, 2 is repeated in the path, 3 is not repeated. So are you having a path from 5 to 3, previous to current 5 to 3 path is there, so select it. Again call the return and call the Hamiltonian of the 5. So when I will call the Hamiltonian of the 5, again I will start with the 0. So next higher vertex 1, it is repeated here, 2, it is repeated here, 3, it is repeated here, 4, it is not repeated. Are you, it is unvisited? Yes. Are you having a path from 3 to 4? 3 to 4, yes, path is there. Okay. Finally, I will check that are we having a path from 4 to 1, because I should come back to the same starting vertex, no? Yes, 4 to 1 is also path is there. So I will consider this as my one of the Hamiltonian path or a cycle. Now, whatever I have explained you, so that is, I will now go through the algorithm. So initially I will call the Hamiltonian of the 1. So I will come here, next value of 1. So I will move to the one more function, next value of 1. What is the purpose of using the next value of 1 is that it will check that whether it is a legal vertex or not. Can I consider that vertex or not? So then I will go to the next value. So when I will come to the next value here next value of 1, I will come x of 1. So x of 1 is equal to x of 1. Initially what all will be an assigned? All will be an assigned with the 0. As I told you already, all will be an assigned with the 0. So what is my x of 1? 0. 0 plus 1 is 1. 1 mod 6. N is nothing but number of the vertices plus 1. So it is 1 mod 6. 1 mod 6 is 1. Okay. So now I am checking whether the x of the k is equal to 0. So is x of the, now what is my x of 1? It is 1. So that is what x of 1 is now, it is 1. Here tracing also it is done. So what is my initially I'll call Hamiltonian of 1, I'll come to the next of 1, then I'll call x of the 1 is x of the k plus 1 mod of 6, that is 1 mod 6, that is equal to 1, that is equal to 1. So now where I'll move and then I'll check whether the x of the 1 is equal to 0. No, it is 1. Okay, then if it is equal to 0, then I'll go to the main function. Otherwise, I'll continue with this one. So now I'll come to this one. So are you having a edge from, what is x of the 1? 1. So what is x of the k minus 1? What is my k? 1. 1 minus 1 is 0. You are not having a 0th vertex. Then obviously there will not be a path from 0th vertex to the first vertex. Okay. So this condition will be an false, and again I'll return back to the main program. So when I'll come to this main program, so what I am checking here whether the x of the 1 is 0. No. Okay. Then I'll check whether the k, what is k? 1 is equal to 5. No. 1 is equal to 5. So then what I'll do, I'll go to the else part, I'll call the, so this is not true. Okay, this is not true, this is not true. So I'll come to the else part, Hamiltonian of the k plus 1, that is 1 plus 1. That means I'll call the Hamiltonian of the 2. That means I'll call the Hamiltonian of the 2. Initially this is also 0. Then I'll call the, then I'll go to the next highest vertex, So that is what I'll do. So Hamiltonian of 2, then immediately Hamiltonian of the 2 will call the next value of an 2, and the next value of an 2 when I'll come here. So it is 0 plus 1, because x of 2 is initially 0 only, no? So 0 plus 1, 1 mod this one, so it is 1. So when I'll come to this particular condition is when it is a last vertex. Already 5 vertices I have visited, then I'll come here. It is 5 plus 1, that is last vertex means 4th. 4 plus 1 is 5. 5 mod, last vertex means 5 vertices are there. No? Last vertices means it is 5 plus 1, 6. 6 mod 6 is 0. Means when I have finished all the vertices visited, then this will become true. Until that one, this will become false. So we are still in the second vertices only. Then obviously this will not be a true. Then I'll come here. Now I'll check that are you having an edge from 1 to 1? Yes, we are having an edge from, or we are not having an edge from, that is also fine. So here I am checking, are you having an edge from 1 to 1? No. Means I'll come to the else, then I'll go back to this. Sorry, are you having, what I told, there will be an edge from 1 to 1, 2 to 2, 3, 3. Therefore, are you having edge from, what is this k minus 1? What is my k? 2. 2 minus 1 is 1. So x of 1 is how much? X of 1 is 1. Okay. Now what is this? I got x of the k. What is my x of k? What is my x of the k? So it is also 1. Here still I am in this case. Okay. Are you having an edge from 1 to 1? Yes. Then I'll enter here. Now I am checking whether it is a distinct element or not. So j is equal to 1 to the k minus 1. So what is 1? K? K is 2. 2 minus 1 is 1. So only 1 will be there. J is equal to 1. So what is x of 1? It is 1. X of 1 is, where it is? X of 1 is 1. What is x of 2? It is 1 only. Still I am in this. So x of 2 is also equal to k. X of 2 is also 1. So both are equal to 1, 1 means then break. Means what? It is not a distinct element. So because these are 2 are not a distinct element. So then what I'll do? I'll not go to the main function. Just a break means I'll break out from this for loop and again I'll move back to this one. Okay. Still I am in the while loop only. So x of 2 is now, what is my x of k? 1. 1 plus 1 is 2. 2 mod 6 is 2. Okay, this is false. Now again I'll come here. Now are you having a path from x of k minus 1? That means I am checking are we having a path from here to here. Yes, there is a path from 1 to 2. Then after checking whether we are having a path from 1 to 2, then what I am doing in this for loop, I am checking that is it is a distinct vertex, means this 2 is it is repeated in the previous entries or not. So anyhow this is a distinct element. Yes, this is a distinct element. If it is same element, then I'll break and I'll go back to this, okay, while loop. But if it is not a distinct element, then I'll come here. So what is this if condition says that this if condition will be executed when, what is my j value, it is 1, what is my k value 2. Here it is not equal, but when this will be usually equal and when this condition will become true means, so when you are when you have visited all the vertices and you are checking that are you having a path from that last vertex to the first vertex, because I have to come back to the same vertex, no. So like this, so here 4 to 1, I am checking when I have visited the last vertex 4, I am checking that are we having a path from 4 to 1. So that is 1, 4 to 1 are we having a path. At that situation you will come, this will become true, this will become true, and I will move back to the main function, that is Hamiltonian function, okay. But in this case it is not the last vertex is what we are visiting, so we will not come to this particular case. So now it is not a distinct element, then this will become false here. Then again I'll move back to the Hamiltonian, this main function. So when I'll come to this main function, x of 2, I am checking that whether it is 0, no. Then what I'll do, I am check whether what is my k value 2, what is my n value, it is 6, 5. So not equal, so I'll not going to print it because still there are vertices to visit. Again else part I'll come Hamiltonian of 3 I'll call. That means I'm calling this Hamiltonian of 3. Again Hamiltonian of 3, initially it will be an 0. Again get to the next higher vertex, next here tracing I have done here. Hamiltonian of 3. Okay. Again I'll come to the next value of a 3. Again 1 mod 6, 1, 2 mod 6, 2, then 3 mod 6. So when I'll come to the 1 mod 1, so edge from 2 to 1 but is there, but 1 is already visited, but 1 is already visited, 2 is already visited, and there is no edge from 3, no edge from 2 to 3. Previous to here there is no edge, no, that's what we have told you, no. 2 to 3 there is no edge, 2 to 4 there is no edge, that's why I'll go to the 5, that is what I have written here. 2 to 3 there is no edge and 2 to 4 there is no edge. So 2 to 5 there is an edge and it is a distinct element, and it is an distinct element. Got it? But it is not the last vertex. We are still in the third vertex only. We are still in the third vertex only. That is what we are doing it here. So this condition will not become false. This will not become true. Again I'll go back to the Hamiltonian. This will also be a not true. I'll go back to the Hamiltonian of the 4. Okay, that tracing I have written here completely. You go through that. Now I'll call the Hamiltonian of 4, then I'll immediately call the next value of a 4. Again I'll start with 1 mod 6 is 1, then but 1 is already repeated here. Then 2 mod 6 is 2, 2 is already a distinct, it is not a distinct element. Then I'll come to the 3 mod 6 is 3, yes, 3 is a distinct element. Are we having an edge from an 5 to 3 we have to, because previous edge is 5, no. So 5 to 3, are we having an edge, that we have to check. That is what we are checking it here. Are we having an edge from an 3 to 5? Yes, we are having an edge from 3 to 5. Then I'll come here, is it is a last vertex what we are checking? No, it is not a last vertex. Again I'll move back to the Hamiltonian of the what is that, Hamiltonian of 5. So when I'll come to the Hamiltonian of 5, next value of 5 I'll call. Again I'll come here. So it is next, initially it will be 0. Again it is 1 mod 6 is 1. So that is this one. Next vertex, it is already a distinct, it is not a distinct element, it is repeated. I'll move on to the next one. Again it is not a distinct, here that is what we are checking it here, whether it is a distinct element or not. This for loop is used for that purpose. Here I am checking that whether that particular current vertex is already repeated in the previous path or not. So here 2 is already repeated here, 3 is already repeated here, 4 is not repeated, and then I am checking whether there is a path from that we are doing it here. So whether there is a path from previous to the current vertex, yes. Then it is a distinct element or not, we are checking here. Yes, it is a distinct element and there is a path, means I'll select that one. Now when I'll be selecting that one, I am checking here whether it is a last vertex. Yes, it is a last vertex because already we have visited 1, 2, 3, 5. So yes, it is a last vertex. Then this condition will become true. So this condition will become true means I'll say return. So when I'll return means I'll go to the main program. Now again I'll call the next value of a k. So sorry, this is over. Now I am checking whether the x of the k is equal to an 0. No. Then I'll come. Now k is equal to n. Yes. My k is also last and n is 5. This is also 5 because I am in the last one. No. So x of 5. So yes, both are here equal. Therefore I'll enter here. Here what I am doing, just I am printing the whatever is there in the x of I. So I'll use one for loop and I'll print whatever is there in the x of I. When I am printing that one, what I'll get this path. X of 1 is 1, x of 2 is 2, x of 3 is 5, x of 4 is 3, x of 5 is 4. So finally, and print the 4 to 1. So obviously we will be printing that one, 4 to 1. See here, last I am printing the 1. Okay, so that we are getting the one complete cycle here. So whatever this algorithm is there, it is finding out the one particular Hamiltonian cycle. So in the main program again you call it in order to get it to the one more Hamiltonian part. That is what we are doing it here in the Hamiltonian cycle. Okay, and this is also your lab program. So I'll explain that one lab program. Okay, any doubts are there, you can ask the doubt or you can message me. So that is about your Hamiltonian cycle. So Hamiltonian cycle, they will ask for the tracing. If they'll ask for the tracing, you write this tracing. That is, just write the solution space tree. Don't write this tracing, whatever I have written here. It is only for your understanding purpose. I have written all these tracing portion. Okay. So write the algorithm and if they are asking and the tracing. Okay. And there is no time complexity will be asked on all these backtracking concepts. N-queen, sum of subset, Hamiltonian. Usually they won't ask you what is a time complexity. Okay, thank you.